Hello and welcome everyone. Thank you so much for joining me with this brilliant interest. We're going to be talking about mobile security, as the title already gives away. So I'm going to start with a quick outlook on our time together. So I'm going to start with a quick introduction, which I unfortunately had to cut short a little bit, but it's only theoretical stuff. Don't worry about that. Then I'm going to show you how to get set up to actually test a mobile application on both platforms, Android and iOS. And then I've worked out two scenarios to look at in two kind of different ways in which you might approach an application or a scenario. And that's what we are going to look at on both Android and iOS. So, about me, my name is Sandro. I work with the company Cyllective, and I'm the lead of mobile security pen testing at our company. And I also do some awareness, which I've actually removed from this slide here. We at Cyllective are a security boutique founded in 2013. We consider ourselves to have a highly technical expertise and focus mainly on offensive security services. So with that being said, I'll just start with the introduction to mobile. So what I've stripped out here is the kind of way you go about testing, in the sense that mobile security is not your typical exploits. It's not your typical 0 clicks usually. It's typically much more focused on things like best practices and things that are exposed to the inwards of the device. So I want to start with two specific things that kind of showcase this, and that's certificate pinning and jailbreaking and root detection. And this kind of showcases how mobile security goes both ways. So where in a usual web app, you're just protecting your product, in mobile security, you're also protecting the user against the compromise of his phone. So you might want to protect the data of your application in case your user's phone is compromised by an entirely different application. So with that, I want to talk about certificate pinning for a second, because that's going to come up again. And certificate pinning is exactly such a practice. It's the practice where the phone actually receives a copy of the last known good certification, and this certificate is going to be a part of the application itself. This means that even if the device starts to trust a burp certificate, for example, so the burp suite, the application is still going to refuse this certificate because it has a copy of what it knows the certificate should actually look like. And this is one of these protections, so in case an attacker manages to install his own custom certificate authority on the device of his target, the application is still gonna refuse the traffic being intercepted by this attacker. Same thing with the jailbreaking root detection. This is where the app actively checks whether there is some artifacts related to jailbreaking or whether root is possible on Android, and if so, closes the application. So these protections are all typically client-side. This means that they can be bypassed. They're not bulletproof. With enough time and dedication, they can always be bypassed. But it's merely in place to protect against the immediate exfiltration of data. So if I install a malicious app that somehow exploits my device, at least the applications that implement root detection and certificate pinning are going to be secure. At least in the first place, because the attacker is going to have to put in much, much more work to bypass these protections as with when they were not there. So with that being said, I want to start right away with the setup. I'm going to show the setup in general a little bit. I'm going to start with the test device. So obviously on Android, you're going to be needing a rooted device. It helps. You can go quite far without a rooted or jailbroken device. But in order to perform network traffic and reception efficiently, for example, you're going to need to install certain things as root. So the Android Studio emulator works as well, but the version of the emulator you get with the root permissions doesn't actually have the Google APIs. So you're going to need two emulators, one to pull your application from the Play Store that you want to test, and then one emulator without the Google services, which you're going to perform the testing on. As for the iPhone, it's actually a bit more simple because the jailbreak is not strictly needed, because you can install a certificate authority globally without it being jailbroken. But if possible, it's still preferred because you have so many more options. You can do USB stuff without having to go the network route. You'll see in just a second. So if possible, jailbreak is still recommended. As for the setup, this is a quick introduction on the general setup, what it usually looks like. So you're going to start with burp, which is your typical proxy on your device where you test with, where your traffic goes through, and it's going to start this listener. So typically what I do is I'm going to launch a reverse proxy from the device onto the laptop, exposing the port 8080 on the device as already provided by Burp. And then I'm simply going to tell the device proxy on the device itself to use this localhost port 8080, which then immediately points back to Burp already. So what's also always an option is going the network route directly. So setting your Burp interface to 0000 and then simply specifying the IP address as your device proxy. But I personally don't like it. No reason as to why. I just prefer the cables. So that's why I do the reverse proxy. On Android, it looks like this. You can use ADB to spawn this reverse proxy listener, and then using this ADB settings command, you can simply put this configuration in there and specify the local host in this case. So remember, it's the reverse proxy exposed port on the device, which it's going to have to use as the proxy. On the iPhone, there is one extra step needed. Now, if you've ever jailbroken a device and SSH'd into your iPhone, you might know this step. It's called iProxy, which simply does a forward proxy of your SSH port of the local port 2222 onto the device port 22. And this way, you can then use SSH in place of ADB to do your reverse proxy. So this step essentially does exactly the same. It does the reverse proxy from port 8080 on the device right into Burp on my laptop, just with the extra step needing an SSH tunnel to provide the SSH over USB in the first place. Then on the iPhone, you can't do this via CLI, but you can just go to the Wi-Fi network settings, click on little I, scroll all the way to the bottom, and there you can configure your proxy, which is also being set to the exact same settings, so the local host with the newly forwarded port. Next up, we have to install the Burp certificate authority on the device somehow. Android makes this a bit complicated. Before Android 14, it used to be a bit easier. You just have to get the right hash, put it in the right place, remount something, and then reboot. But this doesn't work anymore. There is some workarounds to still do this manually, but if possible, I don't do these things manually, so I'm actually using a magisk module. Magisk is how you facilitate routing on Android at times, and you can use these modules to do certain things on your device. I'll get to what exactly this module does in just 1 second. So you start off by installing your certificate as a default user. You download it, you can grab it from the Burp website. When you're connected to the proxy, typing in Burp is automatically going to take you to this website where you can download the certificate. So then on your device, you simply install the certificate as a user. But this is not what we want yet. We can test certain things yet. As you can see in the settings here, just search for CA certificate. The setting's going to come up. But that's not what we want yet. For certain apps, it's going to work, but most apps are going to rely on the system trust store as opposed to the user trust store. And to access this trust store, we need to be root. And this is where this magisk module comes into play. If you install this magisk module, all you have to do is reboot your phone, and it's just going to pretend that all your certificates in the user trust store are also part of the system trust store. This way you don't have to do it manually, and you can go the easy route. On the iPhone, it's way more easy for a change. So you can just download the certificate. You can approve it the way you approve usual certificates in device management. And then in system, if you go to general about certificate trust settings, I have no idea why they put this in the about tab, but it's there. You can just switch on the toggle, and then it's going to be globally trusted as a certificate. It's easy as that. And with this setup being complete, you're usually immediately going to see some device traffic flowing through, some telemetry, some App Store traffic, things like that. Now, on to the first scenario. So I try to split up the scenario by the 2 ways you can usually go about testing an application. This first scenario is going to look at the network side of it all, and the second scenario is going to deal with instrumentation and hooking the functions on the device directly. So for this first scenario, we're going to look at non-HTTP traffic. And the scenario we have here is a socket connection. Sockets are used by our friends at Threema as presented yesterday as well. It's why I asked the question about dealing with protobuf, because I had to do this a lot. Then you have your messaging applications, media applications, social media applications. All of these at some point do rely on these sockets. The only problem is that the socket traffic ignores the proxy on the Android. So I've set up this example application. I'm going to start with that quickly. Set up this example application. It doesn't do a whole lot, just one button. It's going to send a hello from Android to the server on this custom socket. The server fits in one Python script, and it's going to reply simply with a hello from server. Now, the problem here is that socket traffic usually ignores the device proxy. So it's only going to be HTTP traffic and maybe WebSockets that are a part of your usual traffic, and the rest is going to go the route it usually takes. And this is only one part of the problem, because we still need to deal with this other traffic format, right? Burp only understands HTTP and WebSockets. And this is where a new tool comes into play. This tool is called NOPE proxy. It stands for Non-HTTP Proxy Extension. It's an extension for Burp, and it provides you with this whole new suite of the same functionality you already have in Burp. So you're going to have a history tab, you're going to have a repeater, things like that, but specifically targeting socket traffic. In this extension, you can then configure extra listeners, kind of per host and per upstream, which are then going to be exposed just as usual with Burp, and then you can use these proxies to pass your socket traffic through. So our new scenario is this. We have our non-HTTP proxy extension, and we have our server, which in this case is not running on my laptop anymore, but picture still counts, right? The extension is going to forward the traffic to the upstream server, and vice versa. It's going to go back into the device afterwards. But now we only have this listener active, and to actually get the traffic into the device, we can use a similar approach. We're going to start with a reverse proxy, again using ADB, but then instead of setting the system proxy, we are going to use IP tables in order to, it's a weird picture, but in order to kind of bend our traffic into our newly created listener. And we're going to do a demonstration on this now. So I've set up a little screen share right here. And I'm going to start off with showcasing the setup as a whole itself, just without the certificate part, because that one takes a bit longer. We are going to start off with our ADB reverse proxy in order to connect the ports. Port 8080 on the device equals Burp port on my laptop, right? So as soon as this reverse proxy is running, we can then set the device proxy itself using this ADB settings, shell settings command. Here we go. We can set the device proxy, and now if we switch to the maybe history tab right here and try to click some things on the Android device. Do I even still have my device here? No. There we go. So if we start to click through things, maybe go on Google, maybe click on certain things, we can see the traffic flowing through. And it's HTTPS encrypted traffic. Of course, we can read it. And this is why the certificate was actually installed on the device itself. So if I go to Magisk right here, this is the module I was talking about, just to showcase it really, really quickly. It's a module right here. As soon as this module is installed and you reboot your device, all of your user-trusted certificates are going to be globally trusted as well. Now, onto the demo application. So I'm going to quickly make sure to get on the server. So this is the application, and if we click connect the server right here, we can see on the server tab here, we get the message, and the Android phone gets the response, hence it says connected right here. Only the traffic doesn't go through Burp. Burp didn't move at all, maybe moved due to some telemetry, but it's not going to be part of this traffic because it doesn't follow the proxy rules. It simply ignores the proxy. So, in order to get a hold of this traffic now, we first set up our NOPE proxy extension. I've already done this, so down here you can see this listener. I just simply have to click enable right here, but it has the listener port, which is the port I chose myself. It has the upstream server, which is the actual server and port this demo application is going to be running on. Now, once this is enabled, we can maybe even move to this history tab already and make sure we can see the results once we're done. And then move to a terminal to get set up again. Here we go. So we're going to repeat the steps again with the reverse proxy and spawn our reverse proxy on this port 31337. And now instead of setting the system proxy, we are going to use IP tables. So I have the command right here, doing it exactly like that. Sure, I trust myself. Here we go. And now this IP tables rule is in there, meaning that all of the device targeting port 1337 on the device is instead going to go to my own port 31337. And now, if I go to the app and click connect to server, the demo gods are not playing with me. Connect to server. Yeah, it's not playing nice with me at all. I'm just going to restart the application, otherwise I'm going to skip that part. Nothing coming through at all. Okay. Yeah, I'm sorry about that. But usually you're going to see the traffic going through there. You have your individual packets that are sent. And what I was also going to demonstrate is that you have this automation tab right here, which really helps if you do testing on serialization formats, for example. Because this example was going to implement protobuf, and in here you can say, okay, before every intercept, send this to protobuf decode, and then after every intercept, you can send it to protobuf encode again. And this provides with a much nicer way of working with all this. But yeah, it doesn't seem to work. I'm not exactly sure as to why. So yeah, I'm gonna ignore this for now and move on to the next part. Sorry about that. I'm gonna unload the extension quickly because it's all Java. And since this extension implements all of Burp's features inside an extension, you're gonna feel that. So I want to disable that and move back to my slides. Here we go. There we go. So next up, as for the iOS example, we are going to take a look at TikTok. And the problem with TikTok is that they have additional encryption. So although you can see all of the individual HTTP packets, the bodies of these requests are going to be encrypted. Not all of them, but the interesting stuff. It's the monitoring and logging stuff. So I wanted to get to the bottom of this. Meaning that our usual way doesn't really work anymore. It's going to look like this a little bit. It's all of these log22 servers. Scaling is a bit off here, but hoping you get the idea. Now, if these request bodies are encrypted, we somehow need a new approach, which is the instrumentation. Meaning that we have some new tool. Well, it's not a new tool, but maybe for you. It's gonna read the arguments of the functions directly. So somewhere in the device, we have an unknown function which does some encryption, and we want to read the arguments to this function. Now, this tool I'm talking about is, of course, Frida. It allows for instrumentation of native applications. Works really well, and it usually comes in these two components. It's at least the ones that I use the most, which is the Frida server and Frida tools. The Frida server is on the device directly and handles the actual instrumentation. So it's going to be the piece of software running on the phone which talks to the individual applications. Frida tools is on my workstation, and it's going to be talking to the Frida server to give it the instructions of what it needs to instrument. The server is installed pretty easily. You just grab the latest packet for the Android architecture you're using, or whatever architecture you're using, and then copy it to the phone, run the executable, and that's it. On the iPhone, it's even a bit easier. You just use your jailbroken package manager and then add the Frida source, and the server is already available to be used there. Just like that. Frida tools itself is installable via a Python 3 package, of course, within a virtual environment. A couple of examples of what you can do with Frida. For one, you have Frida PS, which lists all of the processes on the device. Doing -U is always going to specify the USB device. Some more examples. You have Frida discover, and then with a lowercase f and the bundle ID, you can specify which app. And then Frida is going to start the application, and it's going to trace all of the functions. It's going to say, hey, this function was called 1,000 times, this function was called 500 times, and it's a really nice starting point if you're working with an application. But since this approach hooks every single function contained within the application, it's also not the most stable approach. So even if the application has minimal protection against debugging, this is not going to be feasible anymore. Next up, the tool I work with myself the most is called Frida Trace. It allows for you to specify a keyword with this -i right here. And then with the glob format, you can specify any keyword, and it's going to match all of the functions in the application, create a handler for this function, and then tell you when this function was called. So you can start to go and search for encrypt, and it's going to show you all of the functions that contain the word encrypt, and always print a line when this function was called. Of course, this always supports some other options as well. So you can do functions, Objective-C modules, Java methods, and all of these options, but uppercase actually means that it should exclude the function, which is also kind of neat. And then as for the last example with Frida, it's actually hooking a function. So the actual interception of a function, you could say. And this example is a SSL, so certificate pinning bypass for TikTok. And what's happening here is it simply intercepts on the class TT-HTTP task, so TikTok HTTP task, and it's going to set this flag, skip SSL certification error. And every single time TikTok receives a certificate error, Frida is going to make sure that TikTok ignores this error. I've actually not made this myself. This is by Swift AIO, but his script is broken. So you can't use this, but I've made a fork. I've fixed it. He's not merging it in, sadly, so use it if you want. And as for the explanation here, you can again specify the app you want to launch with the lowercase f, and with the lowercase l, you actually specify the script you would like to run. It's all written in JavaScript. So I'm going to demonstrate this now, hoping it works. This is the iPhone, which is surprisingly still connected. And for the initial setup, we are going to need to run our proxy to facilitate the SSH connection, which was this iProxy command right here. I'm gonna move this to some other window. And then with SSH-R again, this is actually our reverse proxy, which then connects our burp ports or our local port 8080 with the burp port on the workstation. I can run this. And just like that, our proxy is actually running. And if we move back to burp, we can maybe try to request some website, maybe go to Bing or something. I have to restart the screen share. The screen share does not seem to be... Come on. Here we go. Here we go. Perfect. So moving to maybe a web browser, accessing Bing. Again, the setup works as expected, and you're also going to see some maybe basic device telemetry already in here. But we're not here to talk about interception. We're here to talk about TikTok. So what actually happens if I open up TikTok now is it's going to prompt me to log in. Maybe I want to sign up and click create an account, but it's going to tell me the certificate authority is invalid. So this is the actual certificate pinning. My certificate from burp is trusted by the device, but TikTok knows what its certificate should look like, and it says no. It has the last word. We can get around this using this certificate pinning bypass. I'm going to show this for a second. So this is the command right here. We specify the JavaScript file containing the actual interception code with the -lowercase l. We can run this. And as you can see now, each time it overrides the certificate error, it's going to print this line. And if we move back to burp to verify that this works, we can already see there's some more that we get. But if we want to actually click sign up now, so this oftentimes happens. The SSH connection here just fails as soon as I connect Frida, but it's fine. You just have to know that it happens. Here we go. So now we can see TikTok requests coming through, and it doesn't tell us that the proxy connection is invalid anymore. It tells us invalid phone number because it made a successful request. Now, we don't actually care about the network side because we want to hook the functions immediately. I just wanted to showcase this quickly. I'm hoping I get a request to the log server, or maybe this monitoring server is already encrypted as well. Yeah, here you go. So this is the encrypted request that we actually want to read out. So we are going to now disable our device proxy because this way we don't always have to run our certificate pinning bypass in order to work with Frida or try to intercept this function now. So this way I still get the connection, but it doesn't go through my proxy anymore. But what I can do now is I can maybe start to trace some things. I can take a look and see if maybe this encrypt function right here, as I've showcased before, appears somewhere within TikTok. And if it's maybe even called. So it's going to create a lot of handlers for all of these encrypt functions. And as soon as one is called that contains encrypt, we get this print right here. So want to showcase just two more quick demos. We have a backtrace in here, which is a really, really useful function if you have a starting point, but you don't know what to do with it yet. So we have this AES encrypt function, which is actually the first rabbit hole I fell into when I was analyzing the TikTok application. And as soon as you intercept this function, you can say AES encrypt within the crypto module, intercept this. You can tell it to do a backtrace. There's plenty of examples of this online, but it's really, really useful because you then get to know what the flow of the application looks like in general. So I'm going to showcase this for 1 second. Launch it again with the same arguments, backtrace.js. And now every time this AES encrypt is called, it's going to print this backtrace. So if you want to be working with IDA, Ghidra, Binary Ninja now and drag in this crypto module to analyze these functions, this is a really nice place to be when you're starting to work on a problem like this. But now onto the actual solution, which was not one of their custom implementations, but it was actually the implementation of Apple itself. So they are using the libcommon crypto dynamic library. And in here, we can start to hook this function and then ensure that right here, there is always going to be the argument 0 in this function. I'm not going to get into detail with every argument, but this essentially specifies whether it's outgoing or incoming traffic. So then either on leave after the function is performed or on enter before the function is performed, we can try to extract the clear text traffic before or after it's encrypted. So just showcasing this for a second. Here we go. So now as soon as data is passing through this function, either to be encrypted or to be decrypted, it's going to take all of this data and print it to the console. So now we can actually see what encrypted data TikTok is sending home to their servers. All right. Moving back to the slides to wrap this up. So what's the actual outcome of this? So TikTok doesn't do much more telemetry than what's expected. They also don't send encrypted data that's not already contained within the unencrypted clear text traffic anyways. So it's just going to be basic telemetry, events, versions, and IDs, etc. Here we go. So this is the end of my talk. Thank you very much for being here. I'm open for some questions if you have them. And yeah, thank you.